Welcome back to the deep dive. Today we're tackling capacitance.
Oh, yeah, capacitance.
You guys sent in some pretty wild physics notes and diagrams.
Some serious electrical engineering stuff.
Yeah, so we're going to break it all down for you. And, you've probably experienced capacitance firsthand.
Oh, absolutely.
Like that zap you get when you touch a doorknob after walking across a carpet.
Classic static electricity.
Right. And that's capacitance at work.
Capacitance is key to so much tech we use every day.
From tiny electronics.
To massive power grids.
So, okay, where do we even start with something like this?
Well, at its core, capacitance is a conductor's ability to store electrical charge.
Like a reservoir for electrical energy.
Perfect analogy.
Yeah.
The more capacitance, the more charge it can hold at a given voltage.
So is there like limit, like how much you can fill it up?
Well, yeah, think about it. As you add more charge, the electric field around it gets stronger and stronger.
Okay.
And eventually it can ionize the surrounding air.
Ionize?
Basically, the air starts conducting electricity. And yeah, it leads to charge leakage, so you can't charge it forever.
That's where the sparks come in, I guess.
Exactly. Charge escaping.
Okay, so that's capacitance as storage. But how do we actually measure it?
There's a fundamental formula. It's Q equals CV.
Okay, Q equals CV. Break that down for me.
So Q, that's the charge stored on the conductor measured in coulombs.
Okay.
V is the potential difference or voltage measured in volts.
Got it.
And C, our star of the show, is capacitance, and that's measured in farads.
So with this formula, if we increase the voltage, we can store more charge on a conductor.
Exactly. But here's the thing. Capacitance itself, that's fixed for the conductor.
Doesn't change.
Nope. Even if you change the charge or the voltage, it's determined by things like the conductor's size, shape, and the material around it.
So back to our reservoir analogy, like the size of the tank stays the same.
Right. Now let's look at a specific example to really get this.
Okay, hit me with it.
A spherical conductor. Imagine a metal sphere just hanging out in the air. Its capacitance depends on its radius and what surrounds it, in this case, air.
So a bigger sphere, higher capacitance.
You got it. Now, what if we swap out the air for something else?
Like what?
Say, plastic or ceramic materials that can support electric fields differently.
This is where it gets interesting.
Different materials have what we call dielectric constants.
Okay.
This basically tells us how well a material can store electrical energy in an electric field. Higher dielectric constant means more support for the field, leading to higher capacitance.
So our sphere, surrounded by this high dielectric constant material, can store even more charge.
Exactly. And this is the foundation for a crucial component in electronics, the capacitor.
Capacitors. I knew they'd come up.
Also known as a condenser.
Right, found in pretty much every electronic device. But how do they actually work?
So it's a pair of conductors separated by this dielectric material, allowing for even more charge storage. Imagine a second uncharged conductor near our charged sphere. This second conductor changes the electric field, making it easier to store charge on the first one.
So they work together.
And if we ground the second conductor, meaning we connect it to the earth, we can boost the capacitance even more.
Clever. But what about different types of capacitors?
The most common one you're probably thinking of is the parallel plate capacitor.
Right.
Two flat conducting plates parallel to each other with a small gap.
And that gap can be filled with?
Air or a dielectric material.
So how do we calculate the capacitance for this setup?
It's a three-step process. First, we find the electric field between the plates.
Okay.
That depends on the charge density on the plates and the material between them. Then we calculate the potential difference.
Potential difference being?
How much energy is needed to move charge from one plate to the other.
Okay.
Finally, we use those values to get the capacitance.
Got it. But those plates have opposite charges, don't they? Attract each other?
Absolutely. That attraction contributes to the energy stored in the capacitor. We call it energy density or electrostatic pressure. Okay. It's a measure of the energy per unit volume of the dielectric material.
So there's a lot going on in there.
For sure, and the parallel plate isn't the only type out there.
What else is there?
Spherical and cylindrical capacitors, they all store charge using conductors and dielectrics, but with different shapes and uses.
So it's like a whole family of capacitors.
Precisely. Each type has its own formula for calculating capacitance based on its shape and the materials involved, and we can combine them in different ways too, but maybe that's for next time.
You're right, we've covered so much already, but this is just the beginning of the world of capacitance. We'll be back soon to dive even deeper. Welcome back to the deep dive. Last time we were talking about combining capacitors and circuits.
Yeah, series and parallel combinations.
Right, so what's the difference?
Okay, so in a series combination, imagine capacitors connected like links in a chain.
Yep.
The charge on each capacitor is equal.
So the same amount of charge flows through each one, even if they have different capacitances.
Exactly. But the voltage across each capacitor won't be the same. A larger capacitance will have a smaller voltage across it. Think of it like a bigger container holding more at lower pressure.
Interesting. So how do we figure out the total capacitance in series?
Well, because the voltage is divided, the total capacitance is actually less than any of the individual ones.
Oh, really?
We calculate it using the reciprocals of the individual capacitances.
Okay, so that's how we can decrease the overall capacitance in a circuit.
Right.
What about parallel combinations?
Parallel, they're connected side by side like branches of a river.
Okay.
And here, the voltage across each capacitor is the same, like the water level in each branch.
Got the same electrical pressure.
Exactly. But the charge on each capacitor can be different. A larger capacitance will store more charge.
Like a wider branch with more water flowing through it.
Exactly. And calculating the total capacitance for parallel is easier.
How so?
We just add up the individual capacitances.
Oh, that's much simpler. So parallel to increase overall capacitance series to decrease.
You got it. We can fine-tune capacitance for different needs.
Like if we need to store a ton of energy at a certain voltage,
Parallel would be the way to go.
because it lets us add capacitances directly.
Precisely. But let's switch gears back to dielectric materials for a sec.
Okay.
We know they enhance capacitance, but how does it work at the molecular level?
I'm curious about that.
So remember, dielectrics are insulators.
Right.
Their molecules can be polarized, meaning their positive and negative charges separate slightly when exposed to an electric field.
Like tiny little dipoles forming.
Exactly. Now, when we put a dielectric between capacitor plates, these dipoles align with the electric field.
Okay.
And get this actually weakens the overall electric field strength in the dielectric.
Wait, weaken? I thought a stronger field meant more charge storage.
It does, but here's the trick. By weakening the field, the dielectric lets us store more charge for the same voltage.
So it's like it's helping the capacitor store more without overloading.
Precisely. It enhances the capacitor's ability to store energy.
So that's where the dielectric constant comes in.
You got it. It measures how much a material increases capacitance compared to air or a vacuum.
Which have a dielectric constant of 1.
Right, and some materials like certain ceramics and plastics have much higher constants.
So choosing the right dielectric is super important for capacitor design.
Absolutely. It's like finding the perfect ingredient. But there are always trade-offs in engineering.
Like what?
Well, one key factor is breakdown voltage.
Big down voltage.
It's the maximum voltage a dielectric can handle before it starts conducting electricity.
Oh, so like exceeding the pressure limit.
Right. If we go over, the dielectric can fail and cause a short circuit.
We don't want that, so we need to balance the capacitance boost with the breakdown voltage.
For safety and reliability. Now, one more thing about dielectrics.
What's that?
There are forces at play when we insert or remove them from a capacitor.
Oh yeah, we touched on this before. It's like there's this hidden world inside the capacitor.
It's all about electrostatics. So picture this, a parallel plate capacitor with air between the plates. Now we slowly slide a dielectric into that space.
Got it. What happens?
The dielectric is pulled inwards towards the center of the capacitor.
Like the capacitor's grabbing it.
It's all about energy. Inserting the dielectric increases capacitance, but that actually lowers the energy stored in the capacitor.
Wait, how does that work?
The dielectric reduces the electric field strength between the plates, and since energy is related to that field strength, it leads to a lower energy state.
So the system wants to be in that lower energy state. That's why the dielectric is pulled in.
Exactly like nature finding balance. Now, if we take the dielectric out,
There's resistance.
exactly, removing it would increase the stored energy, so there's an outward force related to the change in capacitance.
So it's a two-way street. Pull in, resist letting it go.
All thanks to those fundamental laws of physics. And this force on a dielectric has some cool applications.
Like what?
Things like microelectromechanical systems or MEMS.
MEMS.
Yeah, tiny devices, think tiny robotic arms powered by capacitors, grabbing and moving things at a microscopic level, all thanks to this energy stuff.
Wow, that's pretty amazing. But now I'm curious about charging and discharging a capacitor. How does that actually happen?
To understand that, we need to talk about RC circuits.
RC circuits.
Resistor-capacitor circuit, a resistor and capacitor connected in series. When we connect a battery, the capacitor starts to charge.
So the battery is like the power source.
Exactly, pushing electrons onto one plate and pulling them off the other.
And the resistor.
It controls the charging rate like a bottleneck, limiting the flow.
So a bigger resistor means slower charging.
Precisely. And the charging isn't instant, it happens over time.
Okay.
It's an exponential curve. Initially, the charging current is at its max.
Because there's no resistance from any charge already there.
Right. But as the capacitor charges the voltage across, it increases.
Okay.
It opposes the battery's voltage and causes the charging current to decrease.
So it's like it's pushing back against the battery.
Exactly. That's what creates that exponential curve.
So what about discharging?
We remove the battery from the RC circuit and give the capacitor a path to discharge through the resistor.
Okay.
The stored charge flows back through the resistor, equalizing the charge on both plates.
And this also follows an exponential curve.
You got it. At first, the discharging current is at its max because the voltage is high.
But as it discharges, the voltage drops and the current decreases.
Exactly like a tank emptying out.
Right.
So these curves are key to how capacitors behave.
So how do we measure how quickly a capacitor charges or discharges?
We use the time constant.
Right, you mentioned that earlier. How do we calculate that?
It's just the resistance multiplied by the capacitance, tau equals RC.
Tau. Okay.
A larger resistance or capacitance means a larger time constant.
So longer to charge or discharge.
Exactly. After one time constant, the capacitor is about 63.2% charged or 36.8% discharged.
Okay. And how long until it's fully charged or discharged?
Usually we say about 5 time constants. That's when it's pretty much there.
So the time constant helps us predict how capacitors will behave.
Exactly. It's fundamental to so many applications, but I think that's enough for today.
We've covered so much about capacitors.
From the basics to dielectric circuits, charging and discharging.
It's been quite a journey. Welcome back to the Deep Dive. We've been getting deep into the world of capacitance.
It's amazing how something so fundamental is behind so much technology.
Right. From static shocks to those complex circuits, it's everywhere. So as we wrap up, what are the key things to remember about capacitance?
Well, it all comes down to a conductor's ability to store electrical charge. The more capacitance it has, the more charge it can hold.
At a given voltage.
Right. It's like that storage tank analogy we talked about.
Bigger tank, more storage.
And the capacitance that stores capacity depends on a few things.
Like the connector size and shape.
Right. And the material surrounding it.
The dielectrics.
Exactly. They can really boost a capacitor's ability to store energy.
And that's measured by the dielectric constant.
Right. And we talked about combining capacitors, too.
Series and parallel.
Yeah, to really control the capacitance and voltage in circuits.
What a toolbox for customizing capacitors.
Precisely. And then there's the charging and discharging.
The time constant comes in there.
It's all about how quickly those processes happen.
And it's amazing how these basic ideas lead to so many applications.
From simple timers to complex oscillators.
I've learned so much about capacitors through this deep dive.
Me too. It's been a fascinating journey.
So as we wrap up, is there a final thought you want to leave our listeners with? Something to keep them thinking.
How about this? We've seen how capacitors store energy, but are there limits? How efficient can we make that storage and release? And what new ways can we use this power of capacitance? There's so much potential still to explore.
Great questions. I'll definitely be pondering those. Thanks so much for guiding us through this topic.
It's been my pleasure.
And to all our listeners out there, thanks for joining us on the Deep Dive. We'll catch you next time for another deep dive into a new topic.